It's a great pleasure to be with you here on Zoom and be invited to give a talk to the Harvard School of Public Health, which has been formative for me. That's really been the institution that allowed me to kick off my career and do what I'm doing today and present the work I will discuss now. And before I go on, I would say that while strongly founded on the theory and methods application ideas I learned about at Harvard School of Public Health, the work I will discuss right now is done in collaboration with my previous PhD student, Mathias Janvin, who's now finishing his MD in Oslo, my current PhD student, Gellert Perenni, who's here at me at the École Polytechnique Fédérale, EPFL in Lausanne, and a previous Harvard graduate, Louisa Smith. Well, many of us early experienced and also learned from our parents or caretakers that we sometimes need to be careful because certain diseases, they can transmit between humans. And these basic observations, it's not a huge step from that basic observation to realize that if you want to consider treatment against those communicable diseases, we need to bear in mind the fact that they might depend on social behaviors, the number or fraction of vaccinated individuals or who are vaccinated or not for this particular disease in the population, and the prevalence of the disease, or here I'm talking about infection, so infectious disease itself. From a more jargon perspective or statistical or epidemiological perspective, this also implies that there's interference in the population. We cannot immediately assume that the units are IID, so independent and identically distributed. And there's been a huge effort in the statistical and biostatistical and epidemiological methodology environments to study statistical and causal inference in the presence of such interference. And one way to visualize this is to do this in a simple picture is that in broadly speaking, the infectious status of one individual might in fact affect the infectious status and even the treatment effect of other individuals in the populations. They're connected. They're not independent. But if you go to major randomized controlled trials of treatments against infectious diseases, such as COVID-19 vaccines, to the left we have the Pfizer vaccine, and to the right we have the Moderna vaccine. These trials were all analyzed under the assumptions that units were IID, which is precisely what I said units are not in an infectious disease setting. And this is not the unique thing about COVID. It's not that these studies were rushed or that we just had to do something simple there. This is the routine way of analyzing RCTs, even when the outcomes even if we are in infectious disease settings. Of course, there are certain exceptions, but this seems to be the routine. Okay, so we might accept the premise, or at least I believe the premise is that in the target populations, for example, if you're thinking about here during a COVID pandemic, there is interference. People are not IID. But still, the trials assume IID data, okay? So what could be a reason for this? So these trials on the COVID-19 vaccines, they were performed before the vaccines obviously were available to the public and enrolled in vaccination programs because they had to try them out first. And at that stage, one can imagine that the trial participants were a sparse draw from the fuller population, and thus interactions between the participants in the trial itself, which I tried to just depict in this picture, is essentially not zero, so it's negligible. So you analyze the data as if they were IID. Okay, but if you do that with classical statistical methodology, so you rely on IID assumptions, the implicit superpopulation you're studying seems to be a superpopulation where units are IID. Okay, so that's not the same population that we do have in this world. This is not the representative superpopulation, say, for what the more representative superpopulation would be had we, say, enrolled a vaccination program. Okay, so yes, we might do valid inference, but that's valid inference in a superpopulation without interference. Okay, so just keep this in mind a little bit, and then I'll introduce some very basic and simple notation. I suppose that we here have a vector of baseline covariates, L, and we have a binary treatment indicator, so that's vaccine or placebo at baseline. And I also operate with an exposure indicator. So in this case, the binary exposure is not the treatment. The binary exposure is exposure to the infectious agent, for example, exposure to COVID-19. And we have some outcome of interest, say it's categorical, it could be binary or continuous. I just made it categorical here, but that's arbitrary. So say it's severity of infection. And I would also let superscript denote counterfactual outcomes. So E superscript A is the exposure to the infectious agent had the treatment been fixed to little a. And likewise, the outcome with the superscript A is here the severity of infection had I fixed treatment vaccine to little a. Okay. So I use this notation by implicitly when I'm using this notation, I'm assuming that the units are IID. So I believe that, suppose we believe that we have a sparse row of individuals and that's feasible, say as in the COVID trials. But the problem is still, even if I do valid inference in this superpopulation without interference, there will be interference in the target population, say where the vaccine program is rolled out. So if I look at an average causal effect defined in the superpopulation with no interference, this might not generalize to the target population where there is interference. I could try to circumvene, or I could try to come up with other estimates that I intuitively might believe circumvene some of these problems. So I'm just stating one here, and I'm not going to proceed immediately with it. But what I'm saying here is that suppose I want to look at an estimate where I condition on exposure to the infectious agent. So here on the left-hand side, I look at those who would be exposed under treatment, and I look at their outcome. On the right-hand side, those who would be exposed under no treatment, and I look at their outcome. Okay. The problem with this is not the causal effect in the sense that it's not necessarily a contrast of counterfactual outcome in the same subset of individuals, because those who are exposed under vaccination might differ from those individuals that are exposed under no vaccine. So in general, if I say a causal effect is the contrast of counterfactuals in the same subpopulation of individuals, this would not qualify for that definition. Okay. I could also come up with other estimates, and I will state one here that I'll move on with soon, and that would be a control direct effect. And control here means that I control the exposure status. So in this case, I fix everybody to be exposed to the infectious agent. And in a more infectious disease terminology, this would be called a challenge effect. So I basically could give a COVID-19 vaccine, and just immediately afterwards, I could expose individuals to the virus particles directly. So this is not something that's far-fetched. In fact, this was heavily discussed during the COVID-19 pandemic, among other things, where Mark Lipsitch and others strongly advocated that we should perform such trials. And this is a quote from one of his papers saying that obviously challenging volunteers with this live virus risk inducing severe disease and possibly even death. However, we argue that such studies, by accelerating vaccine evaluation, could reduce the global burden of coronavirus-related mortality and morbidity. So here it seems to by accelerated vaccine evaluation, he means essentially getting results quicker, because you expose people immediately and then you will see results immediately as well. I will now go on and claim that there are also certain other advantages with these type of studies. But even if advocated, they were rarely, if ever, done during the COVID-19 pandemic. There were a few of them, but there are certain problems. So it would almost surely not be allowed to include frail and older or people with comorbidities in such type of studies. And already having volunteers was ethically difficult. So if you go back to David Koch's book on planning of experiments and experimental designs, he already then acknowledged the problem of interference, and one of his sentences was that often, however, it's better to go to some burden, to some trouble to arrange that the different units are isolated. But here I'd say instead of isolating them, we would expose them. So in that sense, it's the reverse of what he said. and rather than to allow interference and to attempt to deal with it by emulating a more subtle design. So he said by doing a more subtle design, but here we would say we might not even be able to do that type of design, but we might be able to emulate it. Meaning that we might need to imagine what is this target experiment that you guys in your environment know very much a lot about already. So I'm not going to go through the basics of target trial emulation. But the idea is that we can emulate, even if we cannot do this type of experiments, we could think about emulating them. And by conditioning or intervening on the exposure to an infectious agent, we somehow, the intuition, which I will try to discuss more about now slightly more formally, is that then we mitigate the dependence on the prevalence of infection, the number of vaccinated individuals, and the social behavior, precisely because we control who are exposed. We say, we make an intervention to expose people, and then it doesn't matter how many were in the observed data or how they acted in the observed data. Okay? And my point is also goes beyond that in the sense that if you consider an intervention on exposure, if I were to tell my mom what is the effect of the vaccine for you, I could tell her, so now I know if you were exposed to the virus, this is the expected effect of the vaccine. So if you were exposed to the virus, this is the expected effect of the vaccine. And you can think about the contrary situation too. What would happen if you weren't exposed? Well, then there should be no effect. That's the implicit assumption we will have, because it should only work against in the settings where you're exposed. Of course, there could be side effects and all these other kind of things, but this is how I present it in a simplified way. This is a conceptualization why this could be an interesting effect. Okay, so all I've said so far is relatively uninteresting if we couldn't identify and thus subsequently estimate effects under interventions on or conditional on exposures. And the obvious problem is that exposure to an infectious agent, whether or not an individual is exposed, is something that we usually don't measure. At best, we can hope to have some surrogates of these things or have some data in certain settings where we're sure that, say, their peers or someone around them had the disease. But in general, we barely have measurement of these things, even in randomized experiments. And this is not so. The ideas I've presented so far, while not being very prevalent in the literature, people have easily discarded these type of ideas of considering estimates conditional on or under intervention on exposure because, as here quote from two prominent people in your department, identification of such estimates generally require a measurement of each person's exposure history during the follow-up, which is rarely, if ever, available. And similarly, Beth Halloran said that considering such estimates might not be easy in practice and might indeed require considerable assumptions regarding who is infected and when, and how infectious the people are and who is exposing them. Okay. So I will argue that, in fact, in certain situations, we can actually make progress in consider effects under interventions on exposure and certain estimates conditional on exposure, despite these claims. So in order to make the argument, let's think about the following. So in certain settings, the exposure of any unit is expected to be independent of or not affected by the treatment received. Specifically in the blinded RCT, if the blinding is successful, so you blind with a vaccine, you give the active vaccine and a sham vaccine, you would hope, because that's the idea of the blinding, that the behavioral patterns in the two arms is similar, hopefully identical, and thus the risk of being exposed should be expected to be identical as well. Here I've defined it as an individual level assumption, but I'm essentially saying that the exposure under no treatment is equal to the exposure under treatment. I argue that in a blinded RCT, that should be a plausible assumption. Okay, and if you make this basic assumption, then there's a very simple argument to show that this estimate I suggested, which is on the second line here, so the contrast of outcome in the exposed under treatment and the contrast of outcome in the exposed under the intervention to give no treatment, is precisely the same as conditioning on the exposure itself, which is equal to the third line, which is a principal stratum effect, the effect in those who would be exposed regardless of treatment. This is not a very deep or interesting mathematical argument. I'm just, for now, going to refer to these estimates under these assumptions as the causal effect conditional on exposure. So I just define this as a causal effect conditional on exposure. And when this condition holds, so there's no effective treatment on exposure, you can actually think about exposure as being some kind of baseline covariance, even if it happens after vaccination. And we can consider effects conditional on this. Okay. If I make one other assumption, so I believe I'm this RCT, so the first assumption does not seem to be too far-fetched. Suppose I'm willing to make this other assumption saying that you cannot get the outcome. So the outcome is deterministically equal to 0 if you're not exposed. So for certain outcomes, such as acquiring COVID-19, you would believe that you cannot acquire COVID-19 unless you're exposed to the virus. For other outcomes, that's obviously false. So the outcome was an indicator of death after 1 year. Of course, you could die from other reasons than COVID-19, and thus exposure to COVID-19 would not be sufficient. But if you're considering specific infectious disease outcomes specifically related to the disease of interest, this might not be too far-fetched. So one way to depicting these type of assumptions is to start with a causal DAG, directed acyclic graph. And the idea was that A does not cause E. We assume something slightly stronger than what you have in a distributional DAG. We did it on the individual level, but suppose A is not affecting E and A is randomly assigned, and then the graph, first graph here should be representative. We can draw a SWIG, and it wouldn't tell us much more in this simple setting, but if we draw so-called or SWIG, or we draw a SWIG for specific instantiations of the exposure, we see something more. Specifically, we see that in the case where the exposure is fixed to 0, there's no effective treatment on the outcome because it's deterministically equal to 0 anyway. So we have a so-called context-specific direct effect, which is nicely illustrated with the SWIG. This is not necessary for any of the arguments I'll give further on, but it's just to illustrate the point that this can be somehow depicted graphically in the beautiful SWIGs, which I like a lot. But it might actually be helpful for certain identification arguments that I won't go into detail to. So that's one reason why I'm depicting this here. Moving further, let's now see what we can get from just using these two simple assumptions. And then under the condition that this is a perfectly executed RCT, so essentially we have marginal exchangeability, positivity, and consistency, which should hold by design and trial. The causal effect conditional on this exposure is just equal to the naive risk ratio in this trial. So meaning that under these two additional assumptions, the relative effects in the trial is equal to the relative effect conditional on being exposed to the infectious agent. So this is, again, a very simple mathematical argument, and it's related to certain interesting known facts in epidemiology, such as if you have a measurement error in your outcome, but this measurement error is still with perfect specificity, then the risk ratio of the erroneous measurement would equal the risk ratio of the true outcome. And it's related to also certain facts that people have seen in other type of studies. But this is not true on the absolute scale. So if I looked at the risk difference, so difference in expected outcomes under treatment versus control in the exposed, I do not have point of mitigation under the same conditions. And very conceptually, you can say that this might allude to some, well, first of all, you should observe that in vaccine studies, mostly relative effects are reported. During pandemics, we talk about the relative vaccine efficacy, that 1 minus the relative risk. And that's probably been common folk knowledge in the environment that these relative measures are more stable than the absolute ones, without maybe that could be an intuitive claim. And I'm not saying that relative measures are more stable in general. That's not a mathematical fact. But in this sense that this risk ratio is the same regardless of the probability of exposure, that's true. But this is not true on the absolute scale, alludes to maybe some stability properties precisely in these settings, if you believe in the assumptions I've made. Okay, so how about maybe a better interpretable estimate? So the previous one was quite easy to identify. Let's think about now the causal control direct effect, or the so-called challenge effect, which is defined on an intervention on exposure, not conditioning on it. So the aim here is not to give you a basic causal inference course, but it's a known and fairly straightforward causal inference identification result for control direct effects, saying that under classical conditions, this estimate can be expressed as this functional observable data, observable random variables. But the problem is, of course, that I cannot observe this thing, because the remarkable fact with the previous slide, or the remarkable detail with the previous slide, was that we could express a functional that's dependent on, that's defined with respect to exposure status as something that didn't include exposure status at all. So this quantity, while even this looks like an identification formula, this is not computable, because I don't know who were exposed or not. But if I do add these classical conditions for control direct effect identification, which require more assumptions about unmeasured confounding than the previous one, and I add on these two assumptions I described, so the exposure necessity, we do need to be exposed in order to experience the outcome, and the assumptions that there is no effect of the treatment on the exposure, then the relative control direct effect, conditional covariance, equals to the relative risk ratio, conditional covariance. We need to conditional covariance here because we need to condition common causes of exposure and the outcome for this parameter. So again, it's perhaps slightly interesting that we can identify this estimate conditional covariance, but not marginally. And the reason for that, I'll just say heuristically, is that we don't know exactly how we should weight these conditional estimates to get to the marginal one. We don't know what weight we need in order to collapse them into a marginal estimate, because these weights will depend on the exposure distribution. So you can find conditional, but not marginal effect. Okay, so this seems to be somehow fun fact based. I've given you some algebraic properties, and the arguments to derive them is quite simple, but now I'll argue that this might actually matter in certain settings, or at least clarify certain notions that are frequently used in clinical papers and also in epidemiology papers, and see how we can clarify the meaning of these notions and concepts. So one of them is waning. So this is taken from some American guidelines or recommendations for COVID vaccination. And here they suggest that certain high-risk individuals should get vaccinated. And their argument is that, among other things, that these individuals might have immunity against COVID-19 that declines faster than other groups of individuals. So this decline of immunity alludes to waning, alludes to declining effect of the vaccine. So you say might need a booster or repeated vaccinations to get protection. Okay. And how do they make such claims? So the classical way of analyzing data, and I would say classical, but at least frequent way of analyzing data and looking at declining rate ratios of outcomes in say an active vaccine arm and in control arm. So now I don't give a COVID example. I could easily find one. There are several ones that analyze data in exactly the same way, but just to show that this also is not specific to COVID, this seems to be in a lot of settings. I took a malaria setup where they gave randomly assigned people. So this is a New England Journal of Medicine publication. They randomly assigned people to an active vaccine versus a mock vaccine, which is rabies. And what they see is that when they look at incidence ratios in the first, second, third, and fourth year, it seems like the protection or the incidence ratios goes closer and closer to 1. Based on that, they conclude that the vaccine efficacy is waning. Okay, and this is the same way many other data that have been analyzed also during the COVID-19 pandemic. Okay, so well, people in this Zoom room has known for a long time that this is not necessarily an adequate way of defining causal effects. And if we believe that waning alludes to something causal, so declining effect of the vaccine, this might not be the adequate way of concluding that the effects actually are waning. And this is related, or in fact, it's isomorphic to the classical problem of the causal interpretation of hazard ratio. And to just show that in the picture, what happens here is that if the vaccine actually did reduce the risk of being infected and having a severe infection, say, then over time, we would expect that the number of the risk profile in those who were uninfected by a certain time, say 1 year or 2 years, is different in the treatment and the control group. And then any contrast of outcomes between treatments and controls, conditioning of being uninfected and unaffected by an outcome by a certain time, will not be a causal effect. Okay, and the intuition might be that this is actually an underestimate and of the true causal effect, and when it's actually an underestimate and not is something that's also interesting to discuss, but not something I'll go into now. But this is also a known fact. This is not something, this has been known by experts in the field for a long time. In fact, even the editor of New England Journal of Medicine, after the COVID-19 pandemic, wrote a piece where he discussed these things. So the previous editor, Rubin, wrote that, I don't think we really are getting at what the immunity is. And so we have to be very careful how we think about waning based on the studies during this. I think was a reaction to the study done during the COVID-19 pandemic. So let's now think about at least one way we can define vaccine waning. And again, I'll have the same setup. So imagine that we have now, again, a binary treatment, vaccine or sham vaccine. And now I will go a little bit beyond the very simplistic setting we had in the first part of the talk, because exposure to an infectious agent is something that happens at a particular time. So now we'll let exposure be a function of time. You can be exposed here at any day, say, or week, or whatever your time interval is defined to be. And the outcome can also happen at each of these time points. So what I will suggest is the following parameter or estimate for describing vaccine waning. And here we define the so-called challenge effect or challenge vaccine waning parameter at some time k as really something that looks similar to a usual vaccine efficacy estimate. So 1 minus some relative risk. But here the risk of infection in vaccinated individuals had we exposed them at time k. So imagine a setting where we expose them at day 5, but until day 5 we isolate them. So we put them in a room so they cannot be in touch with people, and then we isolate them at day 5 or week 5. Versus doing the same thing, so we can put them in a room, and we then look at the ratio of outcomes. We do this with vaccinated and unvaccinated individuals. And we can imagine doing the same, but keeping them in a separated and isolated for 10 weeks instead, and then subsequently expose them to the infectious agent. And a contrast between two different time points, say 1 and 2, should intuitively give us some notion of waning, because they're exposed in the same way. The only thing that's different is the time they were isolated, either for 1 week or say for 10 weeks. And this is different from the conventional estimate, where they don't look at what would happen if we did isolate people and then expose them. They rather look at those who are at risk at every point in time. And then those people who are at risk in the vaccinated group might be different from those in the unvaccinated group because of this depletion of susceptible idea, which I alluded to in the previous figure. Okay. So to describe this more in notation, we can define here a challenge vaccine estimate as a time 1, as what would happen if we gave the vaccine and we exposed at this time versus not giving the vaccine and exposing. And we can look at a similar challenge effect at time 2, where we give the vaccine, we isolate, then we expose. We give no vaccine, we isolate, and then we expose. Okay. And this is just a mere definition, and it turns out that identifying this type of parameter is non-trivial. So under analogous assumptions, so here I mean under the same assumptions as we discussed in the first part of the talk. So we assume that we are in an RCT with these 2 additional assumptions. So no effect of treatment on exposure, perfect blinding. That is perfect blinding. And the other assumption that the outcome can only occur if you're exposed, then it's trivial to identify the challenge effect in the first interval. However, the challenge effect in the second interval would not be point identified under these conditions. We cannot say what it is. We cannot express this just as a function of the observed data. But we can derive bounds So a lower bound and upper bound on this vaccine efficacy. And in most studies of bounds, or well, I shouldn't say most, but in many studies where people derive bounds, the bounds are non-informative in the sense that they become very wide and they're not frequently, well, they, in some sense you can say that they should reflect our true uncertainty in what the value of the parameter of interest should be. Because if you're not willing to assume more and the bounds are sharp, or strict, so they're the narrowest possible bounds, that should reflect our true uncertainty. One problem is that we are not always good in encoding all the assumptions we have about the mechanism we are studying, or the data generating process that generates the vaccine data. But just under these simple assumptions, we can get these bounds. And one intuition for what these bounds are is essentially we can think about we have observed data when certain individuals were infected in the first interval. Suppose there are 3 of them. And when we look at the other interval, we have observations on everybody except these 3 individuals that already had the outcomes. They're taken out, typically. They had the outcome interest. So had we instead isolated all of these individuals, nobody should experience the outcome in the first interval because they were isolated, so they couldn't be infected. And what happens to everybody except these 3 individuals, we know because we knew what happened to them in the observed data. But for these 3 individuals, what could happen is that either they had the outcome, or they did not. They had not had the outcome, or they would have the outcome. So this is what could happen to all of these 3 individuals. The bounds are basically computed in this very naive way by considering these 2 extreme cases. And then we can make bounds in a more sophisticated way as well, but this is the intuition behind it. And if we just use these very simplistic bounds, we see that in one of the major COVID-19 studies, so this was a New England Journal publication on the long-term effect of the Pfizer vaccine. And if we divide into 2 intervals, so I should say that this is rather arbitrary, and this should be seen as an illustrative example. I'm not making bold claims that this is really the right way of doing it. It's an illustration to show that these bounds can actually be informative in certain specific settings. But I'm not.
Yes, it is.
Hello, Bill. Any questions, or later maybe? Yeah. So what we see here is that the confidence interval of the upper bound on the vaccine efficacy, so the most optimistic value of the vaccine efficacy, is tangential to the lower confidence interval of the vaccine efficacy in the first interval, suggesting that the vaccine efficacy in the second interval is smaller than in the first interval. Okay. So this is one illustration. And it seems to resonate with certain previous proposals in the sense that in the more subject matter type of literature, it has been suggested that the right way of studying waning in this context of an influenza vaccine is by enrolling participants to receive a vaccine during a random week. So this is for an influenza that usually starts in November or later, to randomly assign them either in the periods from August to November. And the intuition by that is you randomly assign them before anyone can have the influenza anyway. So this is essentially doing isolation in the way I defined it, but by setting people in a room where they cannot be in contact with people. Yes, sure, that's an extreme thing to do, but a more clever way of doing it is maybe to vaccinate them long before they can even get infected. You can think about the same thing with travel vaccines and stuff like that too. And then contrast the incidence of influenza vaccine between those who were early and late vaccinated. So essentially, the ideas seem to be reflected in the literature. And also, Miguel and others conceptually said similar things to discuss bias. So they didn't necessarily come up with the estimates, but the notion of a target trial is exactly the same for studying booster doses, where they looked at giving booster doses and then looking at whether or not giving booster doses, and then you look at those who didn't get it but had the first dose, and then look at the risk of getting infection later on. So basically, the same idea seems to appear in more practical pieces as well. And I should say that the idea of waning, while discussed a lot in infectious disease settings, I think a similar type of definitions can also be used in other domains of clinical epidemiology. For example, modern antibody-based drugs, they are often speculated to have diminishing effects. also due to autoantibodies, and in cancer cells develop resistance, and we also know that there's widespread human resistance to other drugs for chronic diseases, also blood pressure. So the same ideas can possibly be used in other settings, and might also be relevant when there's no interference. So the last example I will give is using a similar idea, but now the task is many infectious diseases appear in different variants or strains. So COVID, the running example, is one. Depicted some variants here. And one challenge is that these variants, they might appear at different times, and they have different prevalence, and they might even spread to different subpopulations, say by chance. But we still might be interested in what is the effect on these different variants. In fact, there's a literature on these things, which was, I think is heavily based on work by Peter Gilbert. In fact, I think also during his time at Harvard, where he talked about so-called sieve effects, which shouldn't be mixed with sieve estimators in statistics, but sieve effect means really effects on different variants of an infectious agent. Okay, and this is just to depict that during the COVID pandemic, and of course, the variants appeared at different times. We know this, and we all experienced this. And there were great debates about whether the vaccine effect would be different for different variants. So now I will also go away from the setting where the exposure is binary, in the sense that we can have exposure here, say to one variant, say it's Omicron, and the other variant is Delta, or you can be not exposed at all, or possibly exposed to both. And now this can also be generalized to several time points, but suppose we now have an outcome with 3 values. You are no disease, you got infected by Omicron, or you got infected by Delta. We still have a binary vaccine. So now we can again conceptualize a type of control direct effect. It's just that the level of the exposure now is 3 instead of 2, or if you want, a different type of challenge effect. And we can even conceptualize the target experiment here, where we randomly assign people to be vaccinated or not, and afterwards we randomly assign them, or at the same time if you want, but then we randomly assign them to be exposed to either of the variants, say Omicron or Delta. Okay, four-arm trial. And in order to study the relative efficacy, or between relative efficacy on say infection with Omicron versus Delta, we can simply look at the ratio of relative risk. So here's the relative risk in a trial where you're forced to be exposed to Omicron, and here's the relative risk in a trial where you're forced to be exposed to Delta. And we can say that the effect, so the null hypothesis of the vaccine has the same effect on each variant, could be, say, defined as that these relative risks are the same. That's one way of doing it. And notice that if you did this without intervening on exposure, we would run into subtleties, because then the effects could be highly dependent on the prevalence of each variant, on when they appeared, and in which group they were most prevalent. But by controlling the exposure, I think we get closer to a good notion of an effect, or an appropriate notion of effect. But this is not the only one. If you're really interested in the vaccine itself, you might only be interested in what would happen if I vaccinated, because I might, if this is specific to the vaccine and not control, and exposed to Omicron versus vaccinated and exposed to Delta. And in an unpublished article, which is available as a manuscript on arXiv, we discuss how these parameters can be identified under similar assumptions to those I've presented so far. Okay, so if we take it one step back, so in all of these settings, we have appreciated that there might be interference in the population of interest. And thus, even if you're in a randomized trial and you believe that the units do not interfere directly with each other, and therefore you're willing to make conventional IID assumptions when you analyze the data, you are doing inference in a superpopulation where there is no interference. That's what the analysis is based on. And that might not be directly applicable or directly relevant or generalized well to the target population where you might introduce a vaccination program. But I will still argue that these estimates where you control the exposure are relevant to the current world, precisely in the sense that they let you know what would be the effect of the vaccine had we exposed you. On the other hand, it does not give you any clear answers to what would be the effect of implementing, say, a vaccination program in the population, where certainly that effect will depend on interference. But that makes me go on to motivate some of the ongoing work. So some of these assumptions are strong. For example, if we want to use these type of ideas to analyze observational data, we would also need to allow the treatment to affect the exposure status, because we know, for example, during the COVID-19 pandemic, that people changed their risk behavior tremendously after being vaccinated. In fact, there were even restrictions on those who weren't vaccinated. And we also might want to go beyond the assumption that the exposure is dichotomous, that you're exposed or not. We can make it time varying, but the doses of exposure might also matter. And we have made some points about that in the waning paper as well. But the other thing I wanted to go, and that was based on the previous slide, is that when people are fixing or using observed data to inform what the parameters are in compartment models, such as the SIR model and more complicated one. This is the most simple one, as many of you might know, but even a more complicated one, they are using observational data. And what the interpretation of these parameters should be and what type of observational trial data they should use as input to these models is often obscure to me. And one way to clarify it, I think, is to think about them as challenge effects, because these parameters are often given as what would be the effect in those who are exposed and so forth. So I think that these type of parameters might be serving as more clearly defined input to these type of models. And one aim is to go further and actually formalize how we can use these types of parameters as input to the model. So to conclude, I've just today discussed some results on identification of relative effects that can be validly estimated in randomized controlled trials under classical IID assumptions, so the inference is quite easy. And I focus on relative effects, A, because we can identify them, but B, because also that seems to be the parameters that people do report in most vaccine studies, possibly because they feel they're more stable. So in some way, we can think about these results as if you believe in the assumptions, we can now give new interpretations to numbers people routinely compute. And they also motivate certain type of new estimates that might be desirable to know and to study in further work. And in some way, these results might be surprising to some, at least in the sense that even if we don't measure the exposure, we might be able to identify certain effects that are defined with respect to interventions on the exposure or conditional on them. And if you want to see more details, I've highlighted 3 papers here, and I should again reiterate that this is work I've done with Louisa, and these bigger pieces with Matthias, Janvin, and Gellert Preni. So I thank them a lot for this work, and also to the rest of my group at EPFL.